It's 2025, September 18th, approximately 12:17 p.m. So, before my phone ran out of storage, I was here. Therefore, the number of singular matrices is p squared plus open parentheses p cubed minus p close parentheses, which is equal to p cubed plus p squared minus p. Now, subtracting from the total yields that the order of the general linear group with degree 2 over the field with primes is equal to p to the fourth, p to the power 4 minus open parentheses p cubed plus p squared minus p close parentheses, which is equal to p to the power 4 minus p to 3 minus p to 2 plus p. And there we have it. The order of the general linear group with degree 2 over the field primes is equal to p to the power 4 minus p 3, p to the power 3 minus p squared plus p. Right? Let's move on to the next problem. Right. So for problem 8, we are asked to show that the general linear group with degree n over f is non-abelian for any n greater than or equal to 2 and any field f. So what we have to do here is exhibit one pair of invertible matrices that fail to commute, a counterexample. So we do this first for 2 by 2 matrices, then embed those matrices as block diagonals inside an n by n matrix to pass to all n greater than or equal to 2. So, this is naturally kind of an inductive proof. We start with the base case. With n equal 2, set a equal to a equal to 1, 1, 0, 1. Set d equal to 1, 1, 1, 0. Each of these is inside of the general linear group with degree 2 over the field, over some field f, right? So then, as we discovered earlier, dA, which is equal to 1, 0, 1, 1, is not equal to AD, which is 0, 1, 1, 0. Right? So the general linear group with degree 2 is non-abelian. Okay? Now we get to the inductive step. So we assume the general linear group with degree n minus 1 over the field F is non-abelian for n greater than or equal to 3. So there exists x, y within the general linear group with degree n minus 1 over F with x, y not equal to yx. That's our inductive hypothesis. Now, let's form the block diagonal matrices. X tilde is equal to x0, 0, 1. Y tilde is equal to y0, 0, 1. These are both in the general linear group with degree n of F. So, well, then x tilde y tilde is equal to xy 0, 0, 1, which is not equal to y tilde x tilde, which is yx 0, 0, 1. So what does this mean? Well, let me get to that after I erase this. So the general linear group with degree n over some field F is non-abelian. By induction, the result holds for, let me see, result, how fast can I write? Holds for all n greater than or equal to 2. QED. Okay, let's move on to the next one. So for exercise 9, we have prove that the binary operation of matrix multiplication of 2x2 matrices with real entries is associative. So matrix multiplication is built from addition and multiplication of real numbers. And those operations are associative and commutative for addition in the real numbers. So when you expand both open parentheses AB close parentheses C and A open parentheses B C close parentheses entry-wise, you get the same linear combinations of the same products. Let's go ahead and show that a bit more rigorously. So let's let A equal A, B, C, D. Let's let B equal E, F, G, H. C equal I, J, K, L. All of these are within M sub 2, the reals, so the 2x2 matrices. Now, compute open parentheses A, B, close parentheses, C. Well, what do we have for AB? For AB, by standard matrix multiplication, we get AE plus BG. Then we get AF plus BH. Then we get CE plus DG. Then we get CF plus DH. Right? Now, let's multiply that by C. What does that get us? Can we actually write all of that within this space? Let's see. Never know until you try, right? Okay. Open parentheses, AB, close parentheses, times C is equal to, let's see here. Open parentheses, AE plus BG, close parentheses, times I, plus open parentheses AF plus BH, close parentheses, times K, open parentheses AE plus BG, close parentheses, times J, plus open parentheses AF plus BH, close parentheses, times L. All right. And then we go, whoopsies, just realized something. No, wait. Open parentheses CE plus DG, close parentheses, times I, plus open parentheses CF plus DH, times K. Then we have open parentheses CE plus DG, close parentheses, times J, plus open parentheses CF plus DH, close parentheses, times L. All right, so let's keep that in mind and move on to computing A times open parentheses BC, close parentheses. Right? Okay, so let's compute A times open parentheses BC, close parentheses. BC is equal to EI plus FK, then EJ plus FL, then GI plus HK, then GJ plus HL. So let's multiply A by this to get what we want here, to C. Okay. Well, that is equal to A times open parentheses E times I plus F times K, close parentheses, plus B times open parentheses G times I plus H times K, close parentheses, and then A times open parentheses E, J plus FL, close parentheses, plus, B times open parentheses G, J plus HL, right? Now, how about this one next? Well, we get C times open parentheses E, I plus FK, close parentheses, plus D times open parentheses GI plus HK, close parentheses. And then finally, C times open parentheses EJ plus FL, close parentheses, plus D times open parentheses GJ plus HL, close parentheses. Okay? So, what can we make of this? Well, if you couldn't see by now, those things are not equal, but let's be rigorous to almost a fault here. So, entry-wise comparison, well, actually, sorry, did I say these two things don't equal? Not what I meant. So what I meant to say is entry-wise, the exact opposite basically. Entry-wise comparison shows equality. I can just say that was a test to see if you were paying attention. Ha ha ha. No, but for instance, using associativity, and commutativity in R, let me show you this cool thing, right? In the real numbers, what we get is open parentheses AE plus BG close parentheses times I plus open parentheses AF plus BH close parentheses times K. That is actually equal to A times open parentheses EI close parentheses plus B times open parentheses GI close parentheses plus A times open parentheses FK close parentheses plus plus B times open parentheses HK close parentheses, which is equal to A times open parentheses EI plus FK close parentheses plus B times open parentheses GI plus HK close parentheses. Right? And you could do this for all of the other entries, right? So, and similarly for the other three entries. So open parentheses A, B, close parentheses times C is equal to A times open parentheses B, C. Matrix multiplication is associative. Matrix multiplication is associative on 2x2 matrices. 2x2 matrices over the reals. Okay? Now let's move on to question 10. All right, so, just take a swig of water here. All right. So for exercise 10, we have this, which is let G be equal to a set containing matrices like A that are like in the form A, B, 0, C, such that A, B, C are in the reals, and A cannot equal 0, nor can C. Okay? So first off, we're told to compute the product of matrix A sub 1 times, B sub, oh goodness, okay. Yeah, compute the product of A sub 1, B sub 1, 0, C sub 1, and matrix A sub 2, B sub 2, 0, C sub 2, to show G is closed under multiplication. Let's go ahead and do this one part at a time. I could show you all the parts for now, but let's just focus on A. Well, okay. I do have something to say, just sort of like over all of this, though. So, how about I show you all of the parts, and then we'll get into solving them step by step, okay? And then for part B, we have to find the inverse of AB0C and deduce G is closed. It looks like a 6. We have to deduce G is closed under inverses. For part C, deduce that G is a subgroup of the general linear group with degree 2 over the reals. And for part D, prove that the set of elements of G with equal diagonal entries A is equal to C, is to say A is equal to C, is also a subgroup of the general linear group degree 2 over the reals. Okay? So, intuitively for all of these, well, upper triangle matrices multiply to upper triangle matrices, and non-zero diagonal entries multiply to non-zero diagonal. So, closure under multiplication is automatic. Inverting a triangular matrix keeps it triangular with inverted diagonal entries. So, closure under inverses is also immediate. The equal diagonals condition is preserved under both multiplication and inversion. So let's take a look at that a bit more rigorously. Whoops, that almost fell over. Good thing I caught it. I'll just move this that way. Oh no. All right. Let's see about this. Okay, so let me put the eraser here and then put like a marker place here. So let's see. Where were we? Oh yes, I gotta erase this. Right. So for part A, looking at closure under multiplication basically, right? So let's let X be equal to the matrix C, A sub 1, B sub 1, 0, C sub 1, and Y be equal to A sub 2, B sub 2, 0, C sub 2, with A sub I and C sub I not equal to 0, well, then what can we say? Well, let's calculate it out directly. XY is equal to A sub 1 times A sub 2, and then A sub 1 times B sub 2 plus A sub 1, C sub 2, and then 0, and then C sub 1 times C sub 2, which is contained within G, right? Since, and this is, well, because A sub 1 times A sub 2 does not equal 0, I'm sorry, A sub 1 times A sub 2 does not equal 0, and C sub 1 times C sub 2 is not equal to 0 as well. So that does it for part A. Now let's go on to part B. So for part B, we have to find the inverse and deduce G's closed under inverses, right? So it's inverses. Let X be equal to the matrix C, A, then B, then 0, then C, with A, C, neither A nor C equal to 0. So let's seek out the inverse here. Seek the inverse of X in the same triangular form. Okay. Y is equal to X, Y, 0, Z. What would it take for X, Y to equal the identity? Well, let's see here. We have the matrix Cx, which is A, B, 0, C. Matrix Cy, X, Y, 0, Z, which is equal to the matrix Ax, then Ay plus Bz, then 0, then Cz. And we want this to equal the identity matrix 1, 0, 0, 1. So, we basically just solve for each of those. See here. So then Ax is equal to 1 implies X is equal to the inverse of A, Cz is equal to 1 implies C is equal to C to the negative 1, the inverse of C. Ay plus Bz is equal to 0, system of linear equations, right? So which is how you would do this. So it's equal to negative A inverse times Bz. Let's substitute. Substitute Z is equal to C to the negative 1 to get Y is equal to negative A to the negative 1 times B times C to the negative 1. And what do we get? So the inverse of X is equal to Y, which is equal to A inverse, then negative A inverse times B times C inverse times 0 times C to the negative 1. Okay, let's verify this from the other direction. Yx is equal to inverse of A, then negative inverse of A times B times the inverse of C times 0, no, 0, then C to the negative 1, the inverse of C, and then multiply that by X, which is A, B, 0, C, right? So what do we get then? Well, then we get the inverse of A times A plus negative inverse of A times B times the inverse of C times 0. Then for this side, A to the inverse of A times B plus, then there's this open parentheses, negative inverse of A times B times inverse of C, close parentheses times C, and then we have 0 times A plus inverse of C times 0, then 0 times B plus inverse of C times C, right? And what does that get us? Well, it simplifies out to the identity matrix 1, 0, 0, 1. Therefore, the inverse of x is contained within G. Is an element of G. So it's closed under inverses. G is closed under inverses. Let's move on to part C. So for C, subgroup of the general linear group with degree 2 over the reals. Let's look back at what it said directly. So deduce that G is a subgroup of the general linear group with degree 2 of the reals. So we want to show that. And so by A and B, G is both, G is a series of things. It's non-empty, for one thing. It contains I, right? So it's closed under multiplication and inverses. Ergo, therefore, so G is a subgroup of the general linear group with degree 2 over the real numbers. There we go. Oop. All right, on to part D. All right, so for part D, equal diagonal subgroup. Okay, so what did D say explicitly? Well, D said prove that the set of elements of G with equal diagonal entries, that is to say, the case in which A is equal to C, is also a subgroup of the general linear group with degree 2 over the reals. So let's let H be equal to the set containing matrices of the form A, B, 0, A, such that A is within the units of the reals, which is just reals with the exclusion of 0, if I'm not mistaken, and then, so let B belong to the reals proper. Let this be a subset of G. Okay, so if x sub 1 is equal to the matrix A sub 1, B sub 1, 0, A sub 1, and x sub 2 is equal to A sub 2, B sub 2, 0, A sub 2, then x sub 1 times x sub 2 is equal to A sub 1, A sub 2, then A sub 1 times B sub 2 plus B sub 1, A sub 2, then 0, then A sub 1, A sub 2, which is contained within H. Moreover, we just sort of substitute what we had earlier there with the inverse of A for C, and what we get is the inverse of x is equal to the inverse of A, then the negative inverse of A times B times the inverse of A, then 0, then the inverse of A. And that is also contained within H. So, what can we say about that? Well, we can say H is non-empty. It's non-empty and it's closed under multiplication and inverses. That's what I'm trying to write down there. Just okay. And so what can we say then? Well, what makes a subgroup, right? So H is a subgroup of the general linear group with the degree 2 over the reals. And there we go. That's all parts to problem 10. Now let's move on to problem 11. In section 1.4, of course. All right. So let's go back here, set that up. All right. So for exercise 11, let H of F equal the set, be the set of matrices of the form 1A, B, 0, 1, C, 0, 0, 1, such that A, B, C are contained within F, are in F, and let's let X be equal to the matrix 1A, B, 0, 1, C, 0, 0, 1, and Y be equal to the matrix 1, D, E, 0, 1, F, 0, 0, 1, and these are both contained within H of F, right? All right, so this is broken up into multiple parts like the previous one. So for part A, let's compute, we're told compute xy and deduce that H of F is closed under multiplication exhibit explicit matrices with x, y not equal to yx, so H of F is non-abelian. That's part A. Looks like a C, but that should be an A. Okay. So I'm just going to list all of the different parts that we're going to have to do before getting into the intuition and the rigorous look at each of them. So let me just erase this. Okay. So for part B, we have find an explicit formula for x inverse and deduce that h of f is closed under inverses. So this is basically, this is basically most everything we did for the previous problem specified to 3 by 3 matrices. But, so, I mean, there's some interesting things that go within that specific difference, right? So I'll just continue along and list these different parts, and, you can see the difference there. So, closed under inverses. And C, prove the associative law. In h of f. And deduce that h of f is a group of order of f to the power 3 when f is finite. There's a note here, which is do not assume matrix multiplication is associative. All right, moving right along. So let's look at part D, see what part D has to say, see what part D is. So for part D, find the order of each element of the finite group H of the integers mod 2, and part E finally, which is to prove that every non-identity element, see what I mean? These last parts are a bit different. Element of H over the reals has infinite order. Okay, now to get into the intuition of this. H of f is the group of unitriangular 3 by 3 matrices. So multiplication it just adds A's and C's, adds B's with a little carry term, so like AF from the upper right corner. That tiny cross term makes the group non-abelian and also explains the power formulas, which we'll see here in a moment. So let's look at each of these parts breaking down here. So let's see. For part A, closure under multiplication. So let x equal what it was, which is 1a, b, 0, 1, c, 0, 0, 1, and y equal what it was, what we stated it was, which was 1 d e 0, 1, F, 0, 0, 1. Both of those are contained. Whoops. Almost went into the automatic thing of habit there. So let's compute XY entry by entry. XY is equal to, well, 1 times 1 plus A times 0 plus B times 0. All right. And then, well, this is actually going to take up a lot more room than I expected. Let me just erase this and start over with the matrix computation there. XY is equal to 1 times 1, just in case, plus A times 0 plus B times 0. For that, then, well, let me just fill this out here. That's a little bit hard to read, admittedly. Let's see. Okay. So simplifying row by row, which is quite the arduous process here. We get that x times y is equal to 1, 0, 0, a plus d, 1 a plus d, af plus b plus e, 0, 1, c plus f, 0, 0, 1, which is contained within h over f. And if we did the reverse case of this, which is yx, let's see, you already saw the calculations there. But yx is equal to 1 a plus d, b plus dc plus e, 0, 1, C plus F, right? And then 0, 0, 1, okay? All right. If you were to look at these side by side, what you'd notice is that the entry that's in the first row, third column. Okay, so what that is we have AF plus B plus E in XY from XY, right? And we have B plus DC plus E in YX, right? So it's supposed to be an E. Okay. Now, in general, AF does not equal DC. So XY does not equal YX. So, for instance, let's say we have, well, let me go back because I believe that, let me see here. So it is closed under multiplication because each of these things, right, belongs to H over field here. So, but the problem is it's not, well, no, we're supposed to see that it's not abelian, and that's what we found here. And in fact, let's look at a specific counterexample. If you were to claim that it was abelian, here's something which should dissuade you from that, which is x is equal to 1, 1, 0, 0, 1, 0, 0, 0, 1, and y is equal to 1, 0, 0, 0, 1, 1, 0, 0, 1. Well, what we get here then is xy is equal to 1, 1, 1, 0, 1, 1, 0, 0, 1. And yx is equal to 1, 1, 0, 0, 1, 1, 0, 0, 1. So those things are not equal, right? Not abelian. All right. So we have non-commutativity. So we have that H over F is, it's closed under multiplication, sure, but it's not commutative. So let's go and take a look at B, which is about inverses. So let's let x equal 1ab, 0, 1c, 0, 0, 1, which is inside of the h of f. Okay. Seek x to the -1, the inverse of x in the same shape. And we do this in the same general way that we did before, right? Which is to multiply some y, which in this case 1 x y 0 1 z 0 0 1 is what we'll have for that. And we want to solve from x, y is equal to the identity matrix, right? So we do it in the same way in which we did the previous one with a few extra steps because it's 3 by 3 and not 2 by 2. And what we'd end up getting here is that, xy is equal to the matrice C, 1a plus x, af plus b plus y, then 0, then 1, then c plus z, then 0, then 0, then 1. Okay? Now, and set it equal to the identity, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. So, a plus x is equal to 0 implies that x is equal to negative a. C plus z is equal to 0, which implies z is equal to negative c. AF plus b plus y is equal to 0. All right? But here f refers to the second row, third column entry of y. Which is to say that is z. So we'll have to substitute z with negative c. Okay? So let me just clear the board again and then move on to that. So az plus b plus y is equal to 0 implies a times open parentheses negative c close parentheses plus b plus y is equal to 0, and that implies y is equal to ac minus b. So the candidate inverse then is the inverse of x is equal to y, which is equal to which is equal to 1, negative a, ac minus b, 0, 1, negative c, 0, 0, 1, right? So let's verify it from the other direction to make sure. Okay, let me just erase this. And what then do we have? Well, y times x at the end of it, which you'll find, let's see here. 1, open parentheses, negative a, close parentheses, plus a, open parentheses, ac minus b, close parentheses, plus open parentheses, negative a, close parentheses, c plus b. And then 0, 1, negative c, okay? And then 0, 0, 1, which is, in case you didn't know, 1, 0, 0, 0, 1, 0, 0, 0, 1, which is exactly what we wanted to get. So H over the field F is closed under inverses, right? And we have what our inverse is equal to. Already showed that, not gonna write it down again. At least for now. Now let's move on to associativity. Save the best one for last, right? This problem is taking up multiple pages. I mean, in comparison to some of the other ones, it's not too bad. Let's take a look at that. So, associativity and size for C. I'll have to swap this out for this other one here. Associativity and size. Let's compute both. Open parentheses, xy, close parentheses, times z, and x times open parentheses, yz, close parentheses, with z being equal to 1 gh, 0, 1 I, 0, 0, 1, right? So let's use the product from A. Let's not burden ourselves with too much work here, so that we don't need to repeat. X, Y, Z is equal to 1, open parentheses, A plus D, close parentheses, plus G, then AF plus B plus E plus, open parentheses, A plus D, close parentheses, I plus H, right? And then we have 0, 1, open parentheses, C plus F, close parentheses, plus I. Then we have 0, 0, 1. All right, let's go to the other one, which I'll have to erase the forward for. So x times open parentheses, y times z, close parentheses, well, that's just equal to 1, then a plus open parentheses, d plus g, close parentheses, then a open parentheses, oh, okay, goodness gracious. So that's just there to show like their separation. So a times open parentheses, f plus I, close parentheses, plus b, plus open parentheses, di, plus e, plus h, okay, close parentheses. Then we have 0, then we have 1, then we have c plus open parentheses, f plus I, close parentheses, 0, 0, 1, right? So these agree entry-wise. These agree entry-wise. Rearranging terms, right? Under rearranging terms. Rearranging terms. So, multiplication, almost out of time, but in h over f is associative. If the order of f is equal to q, which is less than infinity, each A, B, C has q choices. So the order of h over f is equal to q cubed, right? And I'm going to go ahead and pause here for now. There's still some left to go. We are running out of time for now. We'll pick up with going over part D, and then we'll finish off section 1.4. All right, that's it for now.